I'm convinced that a high potential field, a high electric field, a high electrostatic field reduces the consumption of current required to run a motor coil. I'm convinced it reduces cost and expenditure, even though I don't have a simulation to prove it, that because I haven't tried it out on a motor. But when I look at the situation as I like to imagine it to be, a composition of both the Amman Brothers experiment of 1921 and the Pierce-Arrow-Nikola Tesla experiment of 1931, to me it looks like they're doing the same thing, only more rudimentary in the Amman Brothers execution of their circuit versus a more sophisticated version that Nikola Tesla probably would have implemented. So instead of two copper spheres, he had the electrical analog of two copper spheres, and the so-called 12 radio tubes that Peter Savo witnessed him purchasing in Buffalo, New York when he arrived by train, in fact are none of them are radio tubes, although they are all vacuum tubes. One of them is a diode, two of them are spark gaps, and the remaining 9 are capacitors, vacuum tube capacitors. Only 8 of which are utilized in the circuit, one of which is at the base of the aerial. Here I put it on the front end of the car, to serve as a safety check to disallow voltage from leaving the car from the chassis, because you don't want to lose your voltage to the environment. You want to retain it. But you do have to have an aerial grounding out the chassis, because if you don't, to something other than itself, because if you don't, then the chassis becomes a well, I don't know, it's just for safety reasons, let's put it that way. I'll leave it at that. What else? Now I did some silly things. I took out the 2 coils that used to be here, and I replaced them with capacitors of the same value that are here, and I got better results. So now I've been able to reduce, and then I put another one on this leg to the right of the transformer coil, and then another one to the left of it. The battery's still 6 volts, because that's what batteries were back in the day. And I still have 2 coils versus 2 capacitors on the left-hand side. For some reason, the simulator wants to make this electrical analog for a sphere to be higher voltage and a more active spark gap than this one over on the left. Yet I can't take, in this simulation, I can't take this out and put a ground here to replace it. I have to have this in place. As you'll see in a minute, it does acquire a lot of volts, nowhere near the same voltage as here, and here is more closer to over here, in the megavolt range. You know, this is like hundreds of megavolts, this is a few dozen megavolts, and this is a few hundred volts, I believe, as I recall. It might be a few thousand. In any case, this is the way I'm looking at the envisionment of the thing. Now I've changed the coils on this, which also boosted, because I figured out to myself, this circuit does not connect to the motor directly in a conductive fashion. It's merely magnetically coupled. Remember, the steel drum in the Amman Brothers situation was strapped to the front end of their car. And this leads me to believe that the primary coil over on the left of this transformer is the coil inside the drum, while the secondary coil on the right side of this transformer is the motor coil, magnetically coupled via the chassis and the stator core of a DC motor? No. DC? No, it would actually be the rotor. In a DC motor, it would be the rotor, which makes it kind of difficult, unless they switched and put the coils for a DC motor on the stator, and put the permanent magnets in the rotor, which they could have done. There are, DC motors come either way. So in both cases, the motor coil is the stator coil. And so the stator core is magnetically coupled to the chassis of the motor, and the chassis of the motor is magnetically coupled to the chassis of the car. And so we have to bleed off magnetic charge in the form of electrostatic ionization, or ionization of electrostatic charge on the aerial connected to the car, to dissipate it, because it does help boost the power gain of this thing, although it's isolated. So I'm not sure how to simulate that at the moment, so I don't. But I don't connect the ground directly to the circuit because that diminishes its output in this instance. So at this point, the circuit doesn't have a ground, and Microcap doesn't. Microcap agrees with me and doesn't require a ground from me. Really weird. I'm able to get away with these things. Let's see. So the battery is still charged with a trickle charge, though. Yet it's surrounded on both of its terminals with humongous amounts, dozens of megavolts, which might help preserve the battery and even revive it if it's dead. So the motor side of the transformer, the secondary coil, I have as 1 Henry, while the transformer side on the circuit side, the primary coil, is a mere 1 microhenry. And that does boost the voltage, gee, duh. But because this is an electrostatic circuit, the voltage tends to distribute itself. Not evenly, as you'll see in a minute, but it does distribute itself because there's very little current flow within this circuit. In fact, there's very little current flow within this circuit here, the isolated circuit involving the motor coil and the battery. So I'm going on the presumption, it is speculative, but I'm going on the presumption that when you raise the voltage to humongous amounts, you don't need much current. Now, Byron Brubaker told me that when you raise the voltage to ridiculous amounts that Nikola Tesla tended to do in his circuits, his high-tension circuits, it tends to reduce resistance in the windings or in the wire, similar to the effect that would have been achieved had he supercooled all the windings in the wire to 0 degrees Kelvin. This is what I've been told by an electrical engineer. So I'm going on the presumption that, again, the simulator doesn't know the difference, and it maintains the same resistances that it's had before, and so it shows a trickle amount of current taking place, when in fact maybe something else is taking place. So I don't know that. I don't know why a simulator would overlook that feature, but I guess the simulator was not designed for high voltages, because I took this to the near breaking point of matrices singular. So that tells me already I'm outside. Even though I'm borderline at risk, I'm still outside the parameters of what the software engineers of this Microcap simulator expected it to be used as. Now, I think I took it to 200 seconds, if I'm not mistaken, which is the equivalent of 3 minutes and 20 seconds. So that's pretty good by comparison to several thousand seconds or 1,000 seconds that I've previously had to do in previous models. In fact, this is the best version of this circuit I've come up with to date. And it's all because I took out 2 coils here and put in 2 capacitors and added in more capacitors as far as I could take it, in which I would continue to get a gain. I don't get a gain if I take out these 2 coils here and put 2 capacitors here. I actually get a loss, a reduction of voltage. So I did what I could do to maximize my voltage gain in the shortest period of time possible. And it turns out to be 11 capacitors, or 11 vacuum tubes in the circuit, only 8 of which are capacitors. So it's kind of interesting. Now, I don't know how a 3-phase motor works, how you take a single-phase output from a single-phase generator, an AC generator, and convert it into 3-phase. I always assume that the generators at the plant, at the utility plant, have to be 3-phase by design. They have to have 3 coil or 3 sets of coils or 3 coils by design, so that they immediately put out 3 phases that are offset by 120 degrees. I just assume that's the way it works. Now, I know there are digital conversions for DC current into 3-phase AC current, so I don't know the magical engineering feat of doing conversions too well. I know simple things like power factor conversion. I know that much, but when it comes to three-phase, single-phase, it's outside my ability to know because I've never really studied the matter to understand it, so I'm still clueless and confused. So I always look at things in terms of single-phase AC or just simple DC. It keeps it simple for me. And I'm assuming that somebody else will figure out what sense to make of this and make the necessary changes to make it worthwhile for a more efficient three-phase AC motor to be utilized rather than a single-phase induction or a single-phase AC motor. It just, you know, the efficiency, I know that much. The efficiency is improved when you go to three-phase, but I don't know how to do that. So I drew a little picture and I used the elements that are available in Microcap to do that. So when you scale this up, things may shift around in position. So at this scale of the circuit diagram, everything is located in the right place. Let's see, for my little stick figure of a car, because I want to depict, you know, where the 12th vacuum tube goes, namely the vacuum tube capacitor at the base of the aerial. Now normally for radio broadcast you put a coil at the base, and it's called a loaded coil, or loading the aerial actually is what it's called. And I can't remember why. Quite frankly, I forgot. Be that as it may, whatever the reason is, I'll leave it alone because my circuit is a voltage-oriented circuit, so it requires, see, maybe that's the reason why, because a radio broadcast antenna is a device that works off of the broadcast of transverse electromagnetic waves, and I'm not dealing with that at all. If anything, it's probably longitudinal magnetodielectric because there's so little current and so much voltage. I can assume that, probably safely assume that. So it makes sense to put a capacitor at the base of the aerial and not a coil. Because I took out most of the coils. The only coil I left in is this one, and it doesn't even matter. Well, I guess it did matter in this instance what the coil inductances were. So maybe it does matter what the coupling coefficient is. Now, when you have a rotor coil, let's see, a stator coil, with regard to a squirrel cage rotor in a single-phase AC motor, the magnetic coupling between the squirrel cage rotor and the stator coils varies between 50% and 70%, I do believe. So I took it at its lowest point, 50%, 0.5. And I assumed that as my worst case scenario. So I didn't try this out at 70% to see what would happen. How much would it vary, or does it vary? So let's try that. Let's see if I can do this in one hand. Okay, so that's okay. Now I take that out. Now I turn on the nodal voltages, which don't tell us everything, but in this case, in an electrostatic instance, it tells us everything because there's no current. But when you have current, the voltages on the actual components are not going to be the same as the nodal voltages. But when there's no current to speak of, the nodal voltages are about the only thing that can tell you anything in extreme fashion. Let me show you what I mean. There we see 83 megavolts on either side of the battery. So let's see. Go over here. You light up. You're not going to light up for me, huh? There we go. Where are you? 83 meg. No, see, you're not even there. No, you're 100 milli. Where's your voltage? Nano? Nanovolts? Oh my god. Well, that's nothing by see what I mean? No, it's not even nearly the same. Oh my god. Oh, that's the resistor nearby. Oh, that's not the battery. I want the battery. Oh, resistor. Oh yeah, that's the battery. It doesn't tell us anything. Oh, because the voltage is 6. No, it does tell us, yeah. Okay, so that's not going to tell us anything. That battery's the wrong place to look. Yeah, the resistor would be the only place to look. All right, so let's go over to this resistor. Oh, there we go. That lit up. Okay, so the resistor doesn't show us any voltages. 0 volts. That's bizarre. Okay, so that's resistor number 27. So if I do this, and let's see, Alt AP, no, Alt PA. Alright, so let's see, I put in, what was it again? Oh no, I can't remember. Ah, my memory is shot to pooey. Alright. Resistor is 27. Try and remember that. Okay. Alt PA. Alright, so voltage parentheses R27 close parentheses. Alright, so yeah, it was right. The voltage is in the nano range, and then it spikes down to 15 nano, negative 15 nanovolts. That's bizarre. So it doesn't tell you, nodal voltages don't tell you what's happening in the circuit. Well, in the components of the circuit. The components could be saying something completely different. So the node, that means the wire connecting the resistor to the battery, the wire is charged with 83 megavolts. Well, the wire doesn't have any resistance. Oh shit, so you ignore the nodal voltages because that's bizarre. The resistor has 100 milliohms of resistance, a solder joint, and it's indicating a spike of negative 15 nanovolts towards the end of the 200-second simulation. So that tells me that the actual voltage on the nodes is not 83 meg, but it's actually negative 15 volts. Okay? So the simulator has to look at the nodal voltages and decide, okay, now I'm going to max out and give you matrices singular error, but I can ignore them because I should only be looking at the voltages of the components themselves. All right? That's very important. So I just learned it now, so doing this video has been good for both of us. We ignore the nodal voltages. Don't let it scare you. Now, if I do the current on the battery, something very interesting happens. I had to do another circuit because I've seen this happen in LT Spice, and I forgot, is it the same for Microcap? Well, yeah, duh. They both operate in LT Berkeley Spice, or excuse me, in Berkeley Spice. They're just two different flavors of Berkeley Spice. So let me go get this circuit here. So I did a simple little circuit involving a battery, a resistor, ground, and a diode. And I turned the diode around one way or the other, and when I had it pointing downwards, which is with the with the polarity of the battery rather than against it, I got several amps of current. Something like 7 amps, even though it's a 1 volt battery. I should be getting 1 amp, but whatever. I got several amps of current, but when I turn it in this direction, I don't get 7 amps. And the uncanny thing is, what is the sine value of what I get? So let's go look at the battery. I'm only interested in the battery. Where's my cursor? Yoo-hoo, cursor. I don't even know where oh, here it is. So V1s, so I have to plug it in, okay. So I plug in amps, where's the amps? Okay, amps is I for current, V1 is the battery. Now remember, the diode is going contrary to the battery, so it should be charging itself. And what do we see? We see a spike going in the negative, and then it evens out at negative something nanoamps. It looks like it's 7. Negative 7 nanoamps. This shows me that negative polarity means the battery is getting charged. Okay? That's what it's supposed to tell me. That it's being charged with less than 9 nanoamps of current. All right? So let's disengage. Remember that now. Less than negative 9 nanoamps. So let's disengage that. Let's rotate the diode. Whoops, wrong one. Let's rotate it this way. And now I gotta move it with my cursor. Where's the cursor? Cursor, where are you? Okay. Oh shit, now I gotta use both hands for this. Oh. Nope, 2 fingers. Alright, so now I got it going. Supposedly, before it was preventing the discharge of the battery, so it was only less than negative 9 nanoamps, but now I'm encouraging or refusing any other option. I'm encouraging the discharge of the battery. Okay, so let's simulate that. And now let's do the amperage again. So oh, sorry, I'm doing lowercase. You don't get to see it when it's lowercase. There, nice big capital I. Big capital V and a 1. Now what do we got, and where do we got it? Ah, now it's in a different place. But it's still negative. So now we have something less than 108 negative milliamps instead of something less than negative 9 nanoamps. So this shows that negative means the battery is discharging. Now it's discharging in both instances, but very little when I had the diode turned the other way. So negative means discharge on a battery, and positive means charge. It's not the way I would do it. It's not the way I was programmed to think in terms of Paul Falstad's simulator, because he does the opposite. Who would know that... I have a flick here. Who would know that Berkeley Spice does things backwards? And negative means discharge, and positive means charge. So when we run this circuit, let's run it for 200 seconds. And let's bring up the little window. And let's put in I for current, parentheses, BAT for the battery. All right, ready to go? Whoops. Ready to rock? Yeah, ready to rock. Okay. Hit the button. Now, where's the line? Here it is. And it's in the negative range. It's negative nanoamps. Looks like maybe negative 5 nanoamps, but it's actually 9. And then it spikes in the positive direction, which means the battery's getting charged. Finally, just before we hit 200 seconds, the battery is getting 120 nanoamps of charge. Whereas before it started to spike, it was draining at negative 9 nanoamps. Trust me, it's negative 9. I'm not going to bother going there if we, I only have one hand here. So that's the way microcap works. It's a little, all these, misgivings about microcap, it doesn't show you exactly everything you would expect. You got to know how to interpret it. Otherwise, you're going to be lost, like I've been lost. So let's see. So that's the remainder. Oh, so let's look at the nodal voltages, just for curiosity. Not that it means anything anymore. It only means something to the circuit. So in the junctions between the components where there is 0 resistance, we get 500 volts on either side of the spark gap. That's what that means, the vacuum tube spark gap. And then on either side of the vacuum tube spark gap over here, it's 229, nearly 230 megavolts in the gap between the components where there's 0 resistance. Over here, it's 83 megavolts. So it's actually meaningless. It's actually meaningless. And I kept looking at it thinking it was telling me something. Yeah, it's telling me about the simulator. It's like looking under the hood. What's the temperature of the motor, of your engine, I should say, of your engine in your normal car. Okay, it tells you something. it doesn't tell you anything about performance. It's telling you maybe that it's wasting a certain amount of energy. But so what? In this case, it's like you can't avoid it because it's going to be there. The simulator is going to put it there regardless of whether or not it actually is there. And I have to assume it actually is there. If we had wire that has zero resistance, but we don't. So, okay, where is it located? It must be located in the gap between the atoms of copper in the wire and the atoms of solder and the atoms of I don't know what. It must be located in the gaps. That must be where it is, because where else would it be? I don't know in real life. It's got to be somewhere, because the simulator says it's there. So you see, it's all about interpretation. How do we interpret a simulation? And that's the best guess I can make of it, because I'm sure it means something. Is it germane, Do we have to pay attention to it? No. If you're going to go and build a thing, no. Because I've been freaking out people and freaking out myself. Oh my God, this is so dangerous. No. You look at the voltages of the components and ignore the nodal voltages. And this thing is so safe because it produces absolutely nothing. Oh no. Oh no. So the simulation won't allow me to take it to the point where it actually might be useful. Because it's nano figures. It's nothing. It's nanovolts. All right. Let's turn off nodal voltages. Where's my cursor? Just because obviously it's getting in the way. And let's turn the simulation on. Remove this blank screen. Now let's test out, let's see, the voltage, not of the battery, because that's too obvious, but of this resistor right next to it, okay? So we're going to test out the voltage. It tells us that the current was 150 nano amps, yet it had no voltage. Well, that's ridiculous. Why would a resistor have no voltage? So let's click on the resistor and see what we get. We get a voltage that's slightly above the zero, but still in the positive range. Now, we're not dealing with a battery. It only applies to batteries that we have to think in terms of, oh, negative means it's being discharged. So this looks like it's 1 nanovolt is what it looks like on that resistor. So we've got 1 nanovolt on the terminal, on the negative, where's my finger? On the negative terminal of the battery, we have 1 nanovolt, which means we've got 6 volts plus 1 nanovolt on the positive side in reference to the negative side, right? Because it's going to be 6 volts greater. So if we count this as our ground, which is positive 1 nanovolt, then that means over here on the positive side of the battery, it's going to be 6 volts plus 1 nanovolt, in theory. So let's go over here and see if that's what that is. In theory, that's what it should be, right? In theory. If I'm reading this correctly. So let's go over to here. If I can find my, click on here. Nope, still 1 nanovolt. So now we got something worse happening. The battery's not doing anything. It's not contributing to the circuit. It's being, oh, that must be what the nodal voltages are indicating. The nodal voltages, you see, I don't even know if this simulation is worth anything, because it's telling me the nodal voltages are megavolts, but the battery itself is just sitting there and it can't even put out 6 volts. So that means that at the junction between the solder joint separating the battery from the motor coil, the junction at the solder joint is a mere nanovolt, while the empty space between that solder joint and the battery, or the solder joint and probably the motor coil for that matter, or let's just say between the solder joint and the battery, the anode of the battery, is megavolts. I think it was something like 80 or megavolts. And that means it's suppressing the behavior of the battery. The battery can't even contribute voltage like it normally would do. Now, obviously it can't because the diode is going in the wrong direction. So actually so that's why. So let's see. What would happen if we reverse this diode? Let's see. If I can move it here. There. Okay. Let's do another simulation. It doesn't give us matrix singular error. Now, let's just check out the nodal voltages first. Alright, what do we got? We got higher. We got 122, so it went up by like 40 megs around the battery. Meanwhile, around the spark gap to the right, it's gone down from about 200 to 80. And over here, we get 4,000. I can't remember what it was prior. So around the battery, everything has gone up. Well, that kind of makes sense because, now we got the battery discharging. So now we got to find out what is the battery. Let's see. What would be the first thing to find out? Let's find out the voltage on the battery since that's the easiest thing to do. Sorry I didn't do this in advance, but I didn't think of these things. All right, the voltage on the battery. All right, so we have the battery voltage at 6 volts. And they're all 6. So the spike here that we're showing is so small the simulator can't even tell us what it is because all of these are 6.00. So it's something less than 1 millivolt on the spike, which is in the positive direction, which means it is, holy shit, now it's getting charged. Is that the battery? The battery's getting charged? Well, no. Yeah, but very little. So little the simulator can't tell me how much it's getting charged with. But it is... Oh, no. Oy vey. Now I don't know how to interpret what's going on. Oh my god, this is disgusting. I wonder if the amps are going to tell us anything better. Oh, this is so confusing. I literally don't know what I'm doing anymore. Hello. I have no idea what I am doing anymore. Alright, where's our line? Our line is negative and it's 7 amps. It starts at 7.01 negative and it increases to 7.05 and holds there steady. So does that mean it's discharging negative but the polarity of the voltage is positive? That's really screwy. Boy, is that screwy. Oh, that shows they got it backwards. See, because the diode is going in conjunction with the battery and the polarity is backwards. Because under normal circumstances, especially DC of all things, but even AC, the voltage and the current have to be in phase for a normal conventional dissipative-oriented circuit, thermodynamically, conventional circuit. Because that shows there's zero phase relation between the current and the voltage. Here we're seeing negative versus positive. That means 180 degrees phase difference. Even though it's a DC situation, that's telling me, oh, no, that's right, a negative unity power factor. That means the battery is generating power. Oh, that's exactly right. Oh, that is bizarre. Whereas before, when the diode was turned around, the polarity of both the amperage and the voltage were both in the negative, right? It was, wasn't it? Both in the negative, which, but nano, which means the battery was not getting a charge, apparently, I suppose. See, negative means the battery is discharging, even though it's a positive polarity in the voltage. So all we did when we turned the diode around, we reversed the polarity of the battery to be negative voltage, while the current continued to drain just at a reduced amount. So we were not charging the battery at all. Okay. I am curious though. Let's go back and see what happens if I reverse this back the way it was. Whoops, wrong one. Alright. Because I am really curious. Alright, ready to click on the battery to find out what its voltage is. And it's in, oh dear, it's still positive. Gee, it's a good thing I checked this, because oh, wait a minute, what's going on here? We got a little bit of a spike. Now it's a square wave spike, a flat tips. Yeah, these are flat spikes, square waves, which is what? Raising the voltage of the battery. So we're ever so slightly raising the voltage of the battery. Meanwhile, we know what the current was, but we can do it again just to be on the safe side. And I gotta plug it in. Let's see, I, battery. Alright. So yeah, it's around 9 negative amps. So it's still discharging. And then, do we get a spike? Yes, we get it in the positive direction, which means it's being charged. So apparently when the voltage, so the battery always puts out positive 6 volts. But the amperage is a totally different story, because we're trying to show negative unity power factor, that the battery is a generator of power. It's contributing power to the circuit, and that's why they make the amps negative. But when we turn the diode around against the normal flow of current, instead of it discharging 7 amps negative, now it's discharging 9 nanoamps negative, until it gets a spike towards the end of the simulation period in a positive direction, which tells us we're recharging the battery with a spike that amounts, the tip of the spike is 120 positive nanoamps. This great big spike over here. This little one over here, this looks like it's 60 nanoamps positive. So it's trying and it's struggling and it's succeeding over time to charge the battery with a little bit more of a trickle charge. And over time it'll keep doing that. So the nodal voltages are not telling us anything interesting in terms of what we would see in the real world. They wouldn't be there like that. Yet they do change the behavior of the circuit. They change the behavior of the components of the circuit, in as much as it suppressed the voltage so that I couldn't see that humongous voltage on this resistor over here. In fact, I couldn't even see the 6 volts. Even though it's on the battery, it doesn't leave the battery to go to this resistor over here. Only nanovolts. Remember, it was like 1 nanovolt that came over to this resistor. And that one too. And I was expecting to see 6 volts on at least one of those resistors, but I didn't. I saw only the same, 1 nanovolt. So the nodal voltages are there, but they're in virtual reality, which to us means the empty space between the atoms of the materials of construction of the device. And that means that the electric field, there we go. The electric field is megavolts, but the circuit itself is not. Go figure. Wouldn't it make sense? It would stand to reason. The field is the space surrounding the circuit, which includes the space between the atoms of the circuit as well. So that's what the nodal voltages means. It means you've got a humongous electrostatic field surrounding the circuit, and you're going to have the FCC at your doorstep. That's what it's telling me. But while the circuit itself is not the field is so strong, it's not allowing voltage to move around in the circuit, let alone current. Well, yeah, if the voltage can't move around, neither can the current, or actually the other way around. If the current cannot move around because the electrostatic field is preventing it from moving around, then you're not going to get a transfer of voltage from one component to the next, and so the battery is just sitting there, and it's not going to drain itself a whole lot because it's being prevented from doing so. Finally, I got an understanding of what the simulator is telling me. So, if you're in that field, and let's say you're standing barefoot in a puddle of water, you may not want to be there. In fact, you won't be there for very long. A little pile of ashes will be, oh, that's where Vinny used to be. So this is why my intuition is telling me, do this and you won't exist anymore. Well, yeah, that's a nice way of saying die. I'll be incinerated so fast I won't even know what hit me. Oh, how nice. Just what I needed. So how did the Amman brothers get away with it? That's what I want to know. How did Tesla get away with it? I think the only way to get away with it is to have everybody stand a great distance away. See, they were insulated. They were inside the car. The tires are rubber, insulating them from the ground. The aerial is pointing up away from the ground. And when you put a safety capacitor there, this end, the top end of the aerial is like nothing. It's the bottom side that's humongous. So we have to put the capacitor inside the chassis of the car. And so we're grounding the chassis. So now the only part of the aerial that we see is outside the car. The VTC-12 is inside the chassis of the car. So the whole aerial is no different than the voltage potential of the electrostatic field that surrounds it, but hopefully it's ionizing the air, losing some of that electrostatic field if you're driving along, especially at 90 miles an hour. If you put the aerial inside the car and force compressed air in your air intake through manifold, through or across the aerial, and make the aerial a grill work, so as to ionize the intake of air as much as possible that you exhaust out the backside, now you've reduced your electrostatic field somewhat more so than prior, reducing the likelihood of radio interference in your local environment that you are creating. But if you're in the car and you turn the car on, the field comes up with you in the field. So unless by some weird anomaly Tesla, rolled down the windows and he hung his hand out the side of the car, but see, he's touching the chassis. So he's grounded to the chassis. Unless the aerial arcs and shorts out to the earth, which it can't because the capacitor is protecting that from happening. So it's actually, so long as you remain, now if an officer hands you your ticket, and some of them have their ticket in a metallic protective case, and they open up the case and they write the ticket, and then the opening door serves as a nice place. Well, no, actually, you sign the ticket while it's still on the ticket book, but whatever. If he hands you the thing, you're both going to get electrocuted. So that would not be good. Or you chat with somebody and they lean over and touch you or even come close to you. Oh, they're going to get zapped and incinerated even if they come close to you. Unless the chassis is the same voltage potential as the top side of the capacitor, not the bottom side, then the chassis will be the same as the aerial, which will be the same as the surrounding atmosphere, which means if you walk into the field, it might still be a danger if you're not wearing rubber-soled shoes, which they didn't have back in 1931. We had leather-soled shoes back then. It must have been dry ground when they hit a passenger. Not hit, but they stopped at an intersection and a passenger moved across. Now, if he stopped, he might have disengaged the circuit and erased the field. So it's quite possible that when this car comes to a stop, the field diminishes to a minuscule amount, and so then you don't have to worry about injuring anybody or even stepping out of the car, for that matter, or stepping into it. Even though the circuitry is still running, it's not producing its powerhouse of the field. It's the field I got to worry now about. And Tesla had a few accidents, near fatal. So a field can be dangerous, but it's not in the circuit itself. It's repressing the circuit from the transfer of voltage and thus the production of current. And so this circuit can't produce a whole lot of current. It's incapable of it because the field, the electrostatic field, is repressing the flow of current and the transfer of voltage. Now I understand that much. Okay, so little baby steps. That's all I can do, is hope for, is little baby steps. I hope you enjoyed these baby steps that I've taken you along with me. To remind myself what's going on, I decided to look at the wattage of the coil on the left-hand side. That's the coil over here, L1. And despite the very high voltages that are easy to get us to freak out, the wattage is really small. It's dinky. Here's the wattage starts out at 0, and then it arcs up to 6.4 e to the negative 21. Negative 21. As I recall, that's atto, which is 1,000 times less than a femto, which is 1,000 times, a femto is 1,000 times less than a pico is 1,000 times less than a nano, a micro is 1,000 times bigger, milli is 1,000 times bigger than a micro, and then we get to units. So that's not a whole lot of wattage. That means that the impact of that electrostatic field is minuscule at this point in time, at 200 seconds into the simulation. So although it's megavolts, it's meaningless in terms of actual damage it might do to somebody, or radio interference for that matter. Given enough time, if the voltage went any higher, yeah, the wattage would go higher, but it's got a long ways to go. Very long ways to go. Before that ever happens, something will probably arc and short out. In fact, this thing probably is arcing and shorting all the time, just like the old style magneto dynamo alternators in the old cars, dating back to like the 1940s. That arcing is actually useful for recharging a battery, just enough to get it going if like you're starting from a dead battery. So arcing is not, I think the high voltage is going to encourage the arcing prior to it ever becoming lethal or damaging or radio interference for that matter. That's what I'm guessing, because the wattage is so small and the voltage is so high, arcing is going to happen all the time, and so this thing is never going to amass a whole lot of power that could be damaging when it arcs through a person's body or through the airwaves in terms of radio interference. It doesn't seem likely. So I guess I don't have to worry about it. Thought I'd make that little addition here, a little correction to my worries. But that field does seem to suppress the movement of current, and for that matter, the movement of voltage from one node to another within the circuit. Which means since there's no movement, this is certainly not a TEM or a transverse electromagnetic oriented circuit. It's an electrostatic, a longitudinal electrostatic, magnetodielectric oriented circuit. Which means, do we have to redesign the motor? We're told that Tesla had a custom-made AC motor, a three-phase AC motor. Okay, maybe it had three phases, but how do you custom make a motor that's normally designed to operate under transverse electromagnetic modality into a high voltage, almost non-existent current modality? And still, because all of our motors, the power, the torque, is based on the current. It's not based on high voltage. Even though we say, oh, we deliver voltage to the motor, no, it's the conversion of that voltage into current that creates the magnetic field that gives us the torque, so that the current in the coils of the motor does matter, even though we're told it doesn't. It does, because the current appears there, regardless of how we like to lie to ourselves by claiming, no, we are delivering voltage to the motor coil. Yeah, but it's current developing there in the coils that creates the magnetic field that drives the thing up a hill, up a steep incline at 50, 55 miles an hour, up a steep incline. So it really does matter that this circuit cannot produce current. And if that is involving the motor coil as part of the circuit, which is what you normally have to do when you're trying to reach a resonance point of over-unity, you have to include everything, including your load in the circuit. If you don't, then you're kidding yourself that the thing's going to work once you attach a load to it. You can't plug a load into this thing. This is not a generator, a substitute for plugging into the grid or plugging into a battery pack. This is the load and the source combined. And if it's not, then you're kidding yourself into thinking you can plug something into this. Like, oh, I think I'll plug my something into the cigarette lighter. I don't think, well, yeah, it's isolated over here, so maybe you can get away with it, but I don't think so. The way this thing works, the field will collapse, and then you'll see it for what it is. In terms of its transverse interpretation, nothing. Nothing to write home about. It's merely the electrostatic field that is humongous in this circuit. That's the only thing it's managed to do. So the normal behavior of the circuit, not only is it nothing, but it's nothing because it's not allowed to be anything because the field is suppressing it. So I'm not sure how you would redesign a motor to operate mechanically under extremely low nanocurrent, very high megavolt conditions. I have no idea. And still function as a motor, supplying us with mechanical torque that we are accustomed to in today's world, the acceleration that we want. I don't know. And then moving a heavy vehicle, a Pierce Arrow is 4,000 pounds. My car is 3,000 pounds. So, how do you convert that into torque when all you've got is a very high voltage field that's not even in the circuit? It's in the space around the circuit, but not in the circuit itself. It would be some kind of field-oriented motor, obviously, that does not involve the coils in a traditional manner. Probably it would involve the stator. That's why I think it's so important. I've always felt it to be important that the chassis is magnetically coupled to the armature core, the core of the stator armature in the motor, because something to do with the field is going to matter here. And yeah, duh, now I can see, since all we got's voltage and no current to speak of, the field means everything and the circuit means practically nothing, except that the circuit created the field, but that's about it. It doesn't embody the field. See, normally we have a circuit embody the current, and yes, some voltage. But in this case, it can't embody the voltage, and the voltage is suppressing the current, so there's nothing for the circuit to embody, to speak of, except as a causative factor. It's the causation for the field and the maintenance of the field, but it cannot embody the field because there's no current to embody, and there's no voltage differences to embody. So there's no way to notice that the field is there if all we do is look at the circuit and ignore the field. That's the problem I can see. And the coil, does the coil ignore the field? Can we design a motor so that the coil does not ignore the voltage field surrounding it? That's the challenge to redesigning a motor to accommodate this style of circuitry. And people have tried to create electrostatic motors, but they can't get any torque out of it. Probably because they're misdiagnosing the situation. They're trying to get a voltage difference between the terminals of the motor to drive the motor, when in fact, that's not happening here. We just have high voltage on both terminals relative to ground. That's it. So how does the motor know it's in a field of high voltage? It doesn't, if all we do is look at it in electromagnetic perspective. in which you have to have two terminals. But if you've got it immersed in a field, now all your terminals are shorted out, so to speak, electrostatically shorted out with each other, because they're both sharing pretty much the same voltage potential as each other. So how do you get it to work? Well, obviously you got to rethink your plan on how to build a motor or rebuild a motor to live off a field and not a difference, and not a voltage difference, because a voltage difference would give you current in a normal current-oriented motor. And an electrostatic motor would give you voltage difference between the terminals, but we don't have that here. So this is really a different situation, and so it's not enough to just create a circuit, but knowing how to apply it, how to build it, how to make sense in a mechanical world, in a mechanistic sense. What good would the circuit do you? Mechanistically. All right, now that we got our new challenge ahead of us, the circuit is already mapped out. It's a beautiful circuit. What's it good for? That's the next question. How do we make any use of it? All right?